Hello everyone, my name is Alec Dorenkamp and I will be showing you how to solve section 2.5 problem number 36. So this is an initial value problem where the given is that the equation is the fourth derivative of y minus 4 times the second derivative of y equals x squared. And we're also given the initial conditions that are listed on the screen. So first we want to find the complex solution. So substitute the y's with r's, and then if we factor that, we'll get r squared times r squared minus 4 equals 0. And then you'll see that either r squared has to equal 0 or r squared minus 4 is equal to 0. So since it's r squared, there's going to be two r equals 0, which will be important later when we discuss theorem 2 of section 2.3 in just like 20 seconds. R squared minus 4 also has to equal 0. Factoring that, you'd get r minus 2 in parentheses times r plus 2 in parentheses equals 0, meaning that r is equal to 2 and r is equal to negative 2. So moving down, using theorem 2 and theorem 1. First theorem 2, that's for duplicates. So if there's duplicates, it's that part of the complex solution is c1 plus c2 times x times e to the r value times the x. That r value is 0, so that's going to cancel out and just be a 1. And then as well, you're going to add theorem 1 to this, where if there's two distinct values, then you just do c e to the raised to the power of r times x. So in this case, it would be c3 e raised to the 2x and c4 e raised to the negative 2x, because our r values are 2 and negative 2. So that would give us our total y sub c, which is c1 plus c2 times x plus c3 times e raised to the 2x plus c4 e raised to the negative 2x. Now we want to find the particular solution. So that is found by looking at the right side of the initial equation, which is x squared. So initially you would want it to be you would think that you'd want it to be a times x squared plus bx plus c, but the problem there is that they're asking for the fourth derivative up here, which means that we need the highest power of x to be x to the fourth. So we're going to multiply an x squared times everything in here. We take 3 extra derivatives because, well, actually 4, because we need to substitute those values into the initial equation over here. So once we have those derivatives, we'll plug it in. So we'll plug in 24a because that's the fourth derivative, and then subtract 4 times the second derivative, which is 12a x squared plus 6bx plus 2c, and that will be equal to x squared. Once we factor the 4 into the things in parentheses and then separate it by their power of x, we get negative 48a x squared plus negative 24bx plus 24a minus 8c equals x squared plus 0x plus 0. The 0x plus 0 is obviously it doesn't mean anything other than it helps us separate the x values accordingly. So the negative 48a is equal to 1 because the exponent or the coefficient of the x squared on the right side of the equation is 1. Then negative 24b, because that's the coefficient of x on the left side, is equal to 0 because that's the coefficient of x on the right side. And then furthermore, 24a minus 8c is equal to 0 for the same reason. Solving for a, b, and c, we'll get that a is equal to negative 1 over 48 B equals 0, and C equals negative 1/16, because we plug in the A value found before into the 24A minus 8C equals 0 and solve for C. So that plugging in those A, B, and C values up into the original ax squared plus bx plus c, all in parentheses, times x squared, we find out that the particular solution is equal to negative 1 over 48 times x to the fourth plus 0 x to the third minus 16 x squared, which is the same as negative 1 over 48 times x to the fourth minus 1/16 over x, or times x squared. Continuing on, our full solution is going to be the complex plus the particular solution. So that would be y equals c1 plus c2x plus c3 e to the 2x plus c4 e to the negative 2x plus a negative 1/48 x to the fourth minus x squared over 16. We need to take up to the third derivative of this in order to solve, because the initial conditions that were given the initial conditions of the function y, its derivative, its second derivative, and its third derivative. So once you find those derivatives, we can use the initial conditions to solve for C1, C2, C3, and C4, which is our end goal. So using the first initial condition, y of 0 is equal to 1, so that would be equal to the equation y and plug in 0 for x, for all the x values, which would just give us c1 plus c2 times 0 plus c3 times e raised to the 0, c4 e raised to the 0, and then minus 1/48 times 0 minus 1/16 times 0. So all the functions that are multiplied by 0 are obviously eliminated, which would leave us with 1 equals c1 plus c3 plus c4. Next, we look at the first derivative of y's initial conditions, which is 0 is equal to 1. So then we would plug in 0 again into the first derivatives, the first derivative equation, plug in 0 for x, and that would leave us with 1 equals 2 times c3 minus 2c4 plus c2. And then you'll do that for the next two. It's pretty redundant, so I'll spare you having to listen to me explain those. So what's left is we have 1 equals c1 plus c3 plus c4, 1 equals 2c3 minus 2c4 plus c2, negative 1 equals 4c3 plus 4c4 minus 1/8, and negative 1 equals 8c3 minus 8c4. So what we're going to do is we'll start with the bottom two equations, because those each have the same two variables, c3 and c4, and we'll using substitution, we'll solve for c3 in terms of c4. So that c3 in terms of c4 is equal to negative 1/8 plus c4. Then we plug that into the other equation that we're given, which is negative 1 equals 8c3 minus 8c4. So then solving for c4, we get 3/64, and you can see the information on the screen pretty easily. After that, once we have c4, we can plug in the c4 value back into the first equation that we were using, which is negative 1 equals 8c3 minus 8c4, and then solving for c3, we get negative 5 over 64. Next, we use the second to the top equation, the one that we solve for using the initial conditions of the first derivative, which is 1 equals 2c3 minus 2c4 plus c2, which would give us 1 equals 2 times negative 5 over 64 minus 2 times 3 over 64 plus c2. solving for C2 would give us 80 over 64. And then we'll do the same thing with the equation that we found using the initial conditions of the original equation, which is 1 equals C1 plus C3 plus C4. And you'll find that at the bottom right of your screen right now. And then, so that will give us a C1 value of 66 over 64. So we take these C1, C2, C3, and C4 values, and we plug them into the equation that we found at the top. Y equals C1 plus C2x plus C3 e to the 2x, C4 e raised to the negative 2x plus x to the fourth over negative x to the fourth over 48 minus x squared over 16. Doing that, we get the following equation at the bottom of your screen, and then if you want to have a common denominator for all the values, you can have it be a total of 1 over 192 multiplied by 234 plus 240x minus 9 e to the negative 2x minus 33 e to the 2x minus 12x squared minus 4x to the fourth. And that would be your solution.